So I felt the need to do an additional reactions video just to address some of the common mistakes that I'm seeing some of my students make. It's some of the more typical mistakes. It's the sort that everybody makes, but they are easy to correct. So the first mistake that I want to address is the idea of balancing charges before you start balancing the reaction itself. So here's our first example. Silver oxide reacts with lead, and this little parentheses thing here tells you the charge that lead is going to take after we cross that arrow, just like this picture shows. So let's start off by translating what we have. Silver oxide. Silver has a +1, oxide is a -2. Now this is the number one mistake that I'm seeing a lot of my students make, is that you need to balance charges before you move any farther. All of your compounds must sum to 0. In this case, that doesn't equal 0. 1 plus -2 is not 0. I need to multiply that 1 by something in order to counteract this -2. In this case, a 2 will do it. So I need a subscript of a 2 after my silver. Reacts with lead. Now lead, as just a metal, has no charge. It's not until after I cross this arrow that the lead will pick up this +4. So the next time I write lead, he will have his +4 charge. Since this is a compound and a single element, I know this to be a single replacement reaction. Double replacements require 4 different ions. This only has 3. 1, 2, 3. So, single replacement means like replaces like. Positive will replace positive. So where we see this silver, there will be a lead over here on the right side. So there's my oxide, still with a -2 charge. Again, 4 plus -2 does not equal 0. I need some kind of multiplier to get me there. Again, a 2 will do it. And our silver is left out in the cold. The 2 does not get to come because silver is not a diatomic element. So again, make extra special sure that all of your compounds do in fact sum to 0 before you move on and starting to balance these equations. The number one mistake made in balancing reactions is doing something wrong with these subscripts. So if for some reason you have an equation and you just for the life of you cannot get the bloody thing to balance, start looking at your subscripts and your charges. Make sure that all of your compounds sum to 0. Another mistake that I'm seeing is misidentifying the type of reaction. That, I think, harkens back to just vocabulary. So if you know the definitions of all 5 reaction types, I hope that would help with the identification. Single replacements like this, as I previously said, require a compound and a single element. Double replacements require 4 different ions. Combustions have to have that CHO. What else do we have? Synthesis requires 2 single things, kind of like this lead here, and decomposition only has 1 thing on the left side of the arrow. But since we've gotten this far, let's go ahead and balance this equation. I'm going to use the tally method here. I'll use the picture method in the following problem. So I have 2 silvers on the left, so says that subscript right there, but only 1 silver on the right. 1 oxygen on the left. Remember, anything up top here is a charge, not number of atoms. Number of atoms comes from our subscripts here on the bottom. Lead and lead. Left side does not equal right, but we cannot use subscripts to balance number of atoms. You must use coefficients. Coefficients must go in front of a compound. This is the next major mistake that I see, is that our coefficients, coef for short, go in front of a compound. My analogy is that of a 2x4. I can't stick a 2x4 through your shoulders. I would have a dead thing. Similarly, I cannot put a coefficient in the middle of my compounds because I would no longer have what I started with. It would be a dead thing, to continue with the analogy. So, I need 2 silvers over here on the right, so I find my silver. Coefficient of a 2 should do it. On this side, I also need 2 of my oxides. Over here, excuse me. So let's see. I would need to put a 2 in front. I cannot put the 2 in the middle. That would give me a dead thing. So this 2 will distribute all the way through. So it changes both my silver and my oxygen, just like your coefficients in math. That messed up my silver. Means this 2, not good enough. Instead, I will need a 4. Now, left side equals right side, and this equation is complete. Let's move on to another one, if I can get my paper to slide. There we go. Can you see all of that? I believe so. Cool. This one I'll do the picture method for you. So first we have to translate all of our words into symbols. Manganese is Mn. This 3 gives me the charge of our initial cation. And again, make sure we balance charges before we move any further. 3 minus 2 doesn't equal 0. There's nothing I can multiply 2 by to get to 3, so that means I have to take these 2 numbers to the lowest common denominator. In this case, 6. Means my 3 needs to be multiplied by 2, my negative 2 by 3, and that should get me to 0. Reacts with magnesium, who has a 2 plus charge always, phosphate, who has a 3 minus. There's another one that we have to get to a common denominator of 6. Now for identifying the type of reaction, this has 4 different ions: manganese, sulfide, magnesium, and phosphate. 4 different ions means this is a double replacement, which means all of my ions are going to do-si-do and switch partners. So my manganese with his 3 plus charge is now going with the phosphate. Remember, subscripts can only cross the arrow when they are part of a poly, like this phosphate's 4 right here. Plus 3 minus 3, that equals 0. Yay! Next is our magnesium with his 2 plus, goes with our sulfide, 2 minus. Plus 2 minus 2, huzzah! That one also equals 0. As promised, let's do the picture method on this one. I always tell my students, don't feel like you have to use one method or the other. Both of these methods, the tally one that we did here, or the picture one that I'm about to do, will lead you to the same place. Ultimately, the tally method is quicker, but while you're still learning this, feel free to use the picture method. Let me use the same color this time for the sake of time. So let's draw in all of the atoms that we have in our compounds. This one's nice and simple on this side. So let me see. 1 S, 3 S's. Not equal. So to satisfy law of conservation of matter means I need to have more of this molecule on this side. I can't just draw S's. I have to draw more of that whole compound. This is just like having to put the coefficients in front of the compound. You can't go having just somebody's leg. You got to have the whole person. So sulfurs, check. Magnesiums, check. Oh, that's exciting. Phosphori, phosphoruses, whatever. Oh, those don't match. So I need another one of these. 2 phosphorus, 2 phosphate, 2 phosphate, 2 manganese. Now left side equals right. All that's left to do is to count up how many we have of each molecule and put those coefficients in. 1 of these, 1 of these, 2 of that molecule, and 3 of the last one. Looks like I have time to do one more before I run out of my YouTube allotted time. So let's do that one up top there. So translate quickly. Dicarbon hexahydride. Carbon is C, di means 2, hydride is H, hexa means 6. Reacts with oxygen gas. Remember that oxygen gas is one of those diatomic elements that can never be by itself. So it nothing else to bind to it here, so it must have a buddy in the 2. This is a combustion reaction because I have CHO, and that's it. Makes my products CO2 and water. No charges, no muss, no fuss, so now we're straight on to balancing. Remember, for combustions, do oxygens last. It will make your life so much easier. You read that? Kind of, sort of, that light is in the way. Alright, good enough. So, 2 oxygens on the left, or excuse me, 2 carbons, 1 carbon, 6 hydrogens there, 2 hydrogens there, 2 oxygens plus 1 is 3. So let's go ahead and start trying to balance this guy. Start off with carbon or hydrogen, doesn't matter. I'm going to start with the carbon. So, changed my carbon, hold off on the oxygens. Hydrogen, let's see, we got to get to 6, means I need a 3 in front there. So let's see how many oxygens I have on the left. So the 2 also applies to the oxygen. So that would be 2 times 2 is 4 from my CO2. The 3 applies to both. Oh dear, that would not be good. I can't, there's nothing I can multiply that 2 by to get to 7. So these coefficients, not good enough. Well, I'm going to have to change these guys over here somehow. Let's try multiplying it by 2. Let's see, 4 and 12 over there now. So let's see, if I put a 4 in front, that gives me my 4 carbons. A 6 gives me my 12 hydrogens. Now let's see how many oxygens I have. 4 times 2 is 8. Plus 6 times 1 is 6 is 14. Hey, look at that. I can get to 14 with a 7 in front of my oxygen. So be careful in first balancing charges before you start balancing the number of atoms. Make sure that you put your coefficients in front of all of the compounds what you're talking with, and go back and review those definitions on the 5 different types of reactions. This does just take practice, so have faith and keep at it.